So you saw how we have some descriptive statistics that describe central tendency. We also have statistics that describe the dispersion or the spread of the data. The first measure is the range. The range is simply the difference between the largest value in the dataset and the smallest value in our dataset. When you report the range, I will either take that one number difference, or I'll take the largest and smallest value to represent the range. So I'm not going to show you how to do it by hand because it's just simply the largest and the smallest values. But we could do it in R using two different functions, the range and the diff. These functions are good when we're working with a data set that is extremely large. For example, the AVE3 data set that we created at the very start of this presentation is 100 items. If we were working with this 100 item data set by hand, we'd have to scan through it to find the smallest value and the largest value. In many cases, it's kind of impractical. So what we can do is use R to calculate our range. The function for the range is range and then our vector. Just like with some of our other functions, we do have this na.rm equals t option that would automatically remove missing data before calculating the range. But if you generate your own data set, then it's likely that you will not have any missing data inside of it. Now, the range function gives the minimum and the maximum value. If you want to know the difference between the minimum and maximum value, then what we can do is use the function diff on that range. So basically the range is calculated, it returns two values, and then diff will return the difference between the minimum and the maximum values. So for example, let's see how we can do it in R. Alright, so here's our script. We're going to work with dispersion statistics. Alright, and we're going to calculate the range. I'll actually include one extra header for this. Alright, so what I will use is AVE3. It's already been loaded. So here's our data point. So I can see that our smallest value is going to be 0. Largest value looks to be 5, but I'm unsure. So if you type in AVE3 and run it, you should get this. If you don't, if it says AVE3 not found, then scroll up to your top of your script, go to the previous presentation where we talked about central tendency, and run this entire chunk. In this way, we get the same numbers. Alright, so AVE3 is there. So the first way to calculate the range is simply to say range AVE3. And it gives me my range. My smallest value is 0, my largest value is 5. We can obtain the same information by using the summary function too. So if I use the summary function, it gives my minimum value and my maximum value. What if we wanted to report the actual range, so from 0 to 5? How could we do that? Well, we would use the diff function. So diff on the range of AVE3, and that will return 5. That's the difference between our largest value and our smallest value. How useful is range when describing data? Honestly, it isn't very useful. And it's not very useful because range tends to increase as our sample size increases. So as our sample size increases, it's more likely to get more of those extreme values. So if we compare a sample of size 10 versus a sample of size 100 of the same types of measurements, then the sample of size 100 should have a larger range. So range is sensitive to sample size. Also, range is sensitive to outliers. So if we have one extreme data point or two extreme data points, that's going to inflate the range. What we're really interested in is how do most of the data spread around the data, not so much how the outliers fall around our center point, but where do the bulk of the data lie? how big is their spread. So range isn't that useful. Interquartile range is a little bit better. It's better because it's unaffected by outliers, because the interquartile range only looks at the item number. It doesn't look at the actual value, it only looks at the item number. This represents 50% of our data points. So our interquartile range will give us the middle 50. And it's going to be the middle 50 centered on the median. So if we have skewed data, skewed distributions, and we report the median, we should also report the interquartile range. We can calculate the interquartile range by hand by calculating the first and third quartile, or we can let R do it for us. The function in R is IQR, and then our vector. Note that IQR is all capitals, so capital I, capital Q, capital R. This function also has the na.rm function, but again, if you create your own vector, then you typically don't have to worry about missing data and you can leave it off. So let's go back to RStudio to see how we can calculate interquartile ranges. All right, this time we will use AVE1. So we will calculate IQR. So again, I'm just going to check to make sure I have AVE1 in my data set, and I do. So it works. If not, make sure you run that very first chunk to create the AVE1. So our interquartile range is IQR of our vector, and it returns 4.5. That gives us the range, and that range is centered on our median. So we could take our median value, and that's our center point. Then what we could do is add half of this value above it to get our third quartile. We subtract half of this value to get our first quartile. Can we confirm this? Yeah, we'll use the quartile function. Remember, we can specify our probs, or our probabilities. And we want the first quartile and our third quartile. So I'm going to run the entire chunk. Sorry, it's quantile. We're going to run our entire chunk, and we get 12.05 and 16.5. I can check that to make sure that my IQR is the same just by taking the difference between these two values. So 16.5 minus 12.05 gives us 4.45, which is the interquartile range. So if we do it by hand, our values may be different because of the way R calculates these quantiles, but we would still report it the same way. Our interquartile range would be the difference between these two values. Now, would you report it as 4.5? You could. If you're doing it by hand, you can report it as 4.5, or you can report it as 12.05 to 16.5. So I could say my interquartile range is 4.45 or 12.05 up to 16.50. Either answer would be sufficient. So interquartile ranges are good when we're working with skewed distribution or if we have outliers. What if we are dealing with continuous data where we don't have outliers and we are normally distributed? How do we describe the dispersion or the spread of the data? Well, there's a couple different ways, and these ways all lead up to using standard deviation and variances. So to get to that, I'm going to introduce these alternate methods. So the first term is a deviate. A deviate represents the difference between our data point and the mean of the data set. The problem with reporting deviates is that if we're trying to quantify how much deviation we have of the data, it would make sense to kind of take this value for each of our data points and add them all together to get a sum. But when we do that, this actually sums to 0, because when you look at the average, the sum of the when you look at the average, half of the points fall above it, half of the points fall below it. Not only that, but the distance between each point above the mean is going to equal the distance of our points below the mean. So our deviates always sum to 0, which means we can't really utilize them. But what we could do is take our deviate and then square it. So we can take our deviate, calculate our deviate, and then square it, and then add up all of our squared terms. When we do this, we calculate something called the sum of squares, the SS values. The sum of squares is simply the square of the deviates added together. What this does is basically weight each of our deviates based on the distance from the mean. So values that are really close to the mean have a small amount of weight. Values that are far from the mean have a large amount of weight. This is actually pretty decent because we're trying to describe spread of our data, and if we don't really differ from the mean very much, then the sum of the squares is going to be fairly small. We have a small amount of dispersion. But as we start having points that fall far away from the mean, now our spread starts to increase big time, and our sum of squares should increase. Could we use sum of squares to report the dispersion? Yeah, we can, but the problem is that our dispersion is always going to increase with each sample size that we add. So if we have 5 samples and calculate the sum of squares, and then we collect one more sample, so that our sample size is 6, the dispersion for a sample size of 6 will be larger than the sample size of 5. It's just how it works. So is there a way that we can correct it? Yep, we can, and that is a variance. So a variance is also called the mean square. So it's the sum of squares, and then we divide by our sample size, which basically is the mean itself, right? So a mean is the average of our values divided by the sample size. Well, the mean square is the average of our squared deviates. This is going to balance out our large and our small values and starts to standardize it against our total sample size. Now this equation here represents our population level variance because we use the entire population size. But we're normally working with the sample. So because we're working with the sample, we don't have the population parameter. In other words, we calculate the mean when doing the sample. We approximate the mean when doing the sample. And when we do that, we actually lose 1 degree of freedom. That 1 degree of freedom gets represented here in the denominator. So instead of dividing by our total sample size, it's the total sample size minus 1. You can consider it a correction factor, because if we calculate our sample variance, it's going to be a slightly biased estimator, but when we divide by n minus 1, it gets us closer to being unbiased. Is it still biased? Yeah, it is, but it gets us close to being called unbiased. Can we use a variance? Yeah, we can, but unfortunately, the units of variance is the unit squared. So if we measure wing length in millimeter, and we have an average wing length in millimeters, our variance of that wing length is going to be millimeters squared. How do you interpret that? Well, you really can't. So what we do is take the square root of the variance, which gives us the standard deviation. So the standard deviation is the root mean square value. This puts our units in regular millimeters, in regular units, so it's no longer squared, and it makes the interpretation easier. So this is our sample variance equation. Our sample standard deviation is simply this value with the square root. So in R, these values are pretty easy. So if we wanted to calculate the variance, it's just var for variance, and we give it a numeric vector. Just like with our other functions, we can specify na.rm equals t to remove missing data before running the calculation. Standard deviation can be calculated by taking the square root of our variance, which is more typing, or we can do the standard deviation. So just do SD of our vector, and also we have na.rm equals t. So variance, var gives us the variance, SD gives us the standard deviation. So now that we know the function, let's go through and give you some examples of how to calculate standard deviation and variances by hand and also using R. As an example, let's consider this vector of data. I have 6 data points, and we want to calculate our variance and standard deviation. So we have these equations. Variance is equal to the sum of x minus x bar squared divided by our sample size minus 1. You will notice that in this equation we need to calculate our average. So that's going to be the first thing that we do. So our average, if you recall, is equal to the sum of the x's divided by our sample size. The sum of our x's for these data is 36. So our average is 36 divided by 6, or 6. Now that we have the average, we can proceed to calculate the variance. Now I've set up this vector as a table because it's easier to calculate variance in this tabular format. So what we're going to do is calculate the difference between each of our x's and the average. So 4 minus 6 is negative 2. Negative 2. Then 5 minus 6 is negative 1. And then 0, 2, and 3. Then we're going to do x minus x bar squared, which is taking each of the values that we just calculated and squaring those. And then we take the sum of that column as our sum of squares. And I calculated 22. So we have our top, 22. We divide it by our sample size minus 1, and we calculate a variance of 4.4. Our standard deviation, S, is the square root of our variance. So it is the square root of 4.4, which is equal to 2.10. Now I'll note here that for this table, as we progress to doing frequency tables, we could imagine another column of frequency, or n. So this would be our frequency. And for this, each of our frequencies is 1. If we multiply our x minus x bar squared values by 1, we arrive at the same answer. So here's a second example. We have a vector of 8 data points. I've arranged these data points in a table again because it makes it a little bit easier to calculate means and variances. So, but this time, instead of using the variance equation like I did for the previous problem, I'm going to use this alternate equation. So the alternate variance equation is the sum of our x value squared minus our sample size times our average squared divided by our sample size minus 1. So no matter what type of equation we use, we always have to calculate our means first. So our average is the sum of our x's divided by our sample size. Sum of our x's is 73. Our sample size is 8, so 73 divided by 8 equals 9.125. I'm not going to round at this point because I want to have as much precision as I possibly can at the variance. If we were to round at 9.1, then our variance is going to be off just a little bit. So I'm not going to round at this point. If I have a very large number, so a lot of decimal places after it, then I'll round to 3 digits, 3 decimal places, maybe 4 decimal places, and then I'll proceed with the calculations. Alright, so we have our average. Next thing we need to do is calculate the sum of our x squareds. So instead of doing that x minus x bar and then squaring that, I'm going to square each of these values first and then add up that column. So 5 squared is 25, 8 squared is 64, 9 squared is 81, 100 squared is 100, 10 squared is 100, 11 squared is 121, and 12 squared is 144. So those are our x squareds. We will now add up that column. I get 699. So I have 699 as the sum of our x squared. We will subtract our sample size times our average squared. So 9.125 squared, and then we would divide by our sample size minus 1. So using my calculator, I can see that I have 699 minus 666.125 divided by 7. S squared, numerator, reduces to 32.875. So 699 minus 666.125 divided by 7, and I get a variance of 4.696. Our standard deviation is the square root of our variance, which is the square root of 4.696, which is 2.167. So now at this point we could round. For our x's, for our average, I can report it as 9.1. For our variance and standard deviation, it is convention to use at least the same decimal place, if not one more. So if I did standard deviation, I would report it as 2.17. So we just calculated variances by hand. Let's show you how we could do it in R. So what we will do is go back to our script and continue taking notes. So we have example 1. It's the one we did by hand. We calculated a variance of 4.4. So I'm going to create my vector, ex1, where I input in our 6 data points. So 4, 4, 5, 6, 8, and 9. This is exactly what we had in our example. Then if I want to calculate the variance, all that I need to do is issue the var command. And when I run the chunk, I get 4.4, which is exactly what we calculated. If I also want to do the standard deviation, I could do the square root of the variance of the ex1, or I can just run standard deviation of ex1. I'll run this chunk so we get all of the output together, and you can see our variance is 4.4. Standard deviation is 2.0976. Example number 2 works the same way. I first have to make my vector. So 5, 8, 8, 9, 10, 10, 11, and 12. And then I can issue the var command and the sd command. And I get the same output. Now while we're at it, I'd like to show you some added techniques that would help us check some of our work if we were to calculate everything by hand. So we started with example 1 with our ex1. Here's our vector. All right, and let's say we wanted to check our work. Well, we can calculate the mean just to confirm that that's what we calculated. So mean of ex1 gives us 6. And then I can look at our equation. So the top, that numerator, was the sum of our x's, the sum of the x minus x bar squared. Could I do that? Yes. So I can issue the sum and then do this command. All right, but I have to square it one more time. So I want the sum of our squares. So I want to make sure, well, that was correct, that our square term actually falls inside of the parentheses for the sum. When I run that, I get 22, and that's exactly what we calculated for example 1. In example 2, we use that different equation. So using our ex2, there's our vector, we did the sum of the x squares, which again we can do it. We just take ex2 and square it, and what that does is it squares each of the items in our vector, and then we add up the entire vector. So the sum of our squares was 699, which is what we want. And then what we do is subtract our sample size times the mean squared. So I'll do ex2 squared minus our sample size, which I can use ex2, the length of ex2, which will give us 8, all right, times our mean of ex2. But we want this mean to be squared. So what I'm going to do is go ahead and square it, put that in parentheses and square it so that it gets squared before we calculate it. It will also work if we do square inside of the parentheses. And when we run that, we get 32.875. That's exactly how we did it. So here's some practice, 2 different practice problems to see if you feel comfortable calculating means, standard deviations, and variances. So practice problem 1, I have a data set with six data points. I want you to calculate the mean, variance, standard deviations by hand, and then get these data into R and check your answers. For the second one, you could also do mean, standard deviation, and variances if you want and check your answers in R. But for this problem, I want you to calculate the range and the interquartile range of the data. I want you to do this by hand and then get these data into R and check your answers. So pause the video, do this by hand. Once you have the answers, come back and we will review it. So here's how we calculate means, variances, and standard deviations for practice problem 1. I have my 6 data points. First thing we need to calculate is the mean. Why? Because we need the mean in order to calculate the variance. So I will calculate the sum of our data points, 42. We have 6 data points, so our average is 7. And now we can calculate the variance. So we have the 2 equations for the variance. Which one you use is up to you. I like to use the sum of our x squares minus n times x bar squared divided by n minus 1. I prefer this method for two reasons. One, I can square all of our values and add them up fairly easily, and then write that number down and then continue with the rest of the equations. And if I mess up, I can easily go back and calculate some of the x squares again. And the second reason is that my scientific calculator will give me the sum of the x squared values if I input data. And I'll talk more about that in a bit. So if this is the equation that I'm going to use, I have to calculate my x squares. So I've got 25, 36, 49, 49, 64, and 81. The sum of the x squares that I calculate is 304. So I have 304 minus sample size of 6 times the square of our mean. When I simplify, I get 304 minus 294 divided by 5. That's 10 divided by 5, or 2. So the variance is 2. The standard deviation is simply the square root of our variance. So the square root of 2, which is equal to 1.414. So we just saw how to calculate the variance and the means for practice problem 1. Let's do it in R. So practice number 1. I will read the data in as prac 1, and I will create my vector. Read it in. Now I need the variance, and I need the standard deviation, prac 1. And what you see is that the variance is 2, standard deviation is 1.414. And that matches what we calculated by hand. So practice problem 2 asks you to calculate the range in an interquartile range. I also ask you to calculate the median because we will need it in order to calculate the interquartile range. So the range is the easiest of the two to calculate. The range is simply the minimum value and our maximum value. I've already arranged our data from smallest to largest, so our range is 14 to 23. We can also write it as the difference in our highest and our lowest value, which would be 9. Which one you report is up to you. Now for the interquartile range, we have to calculate our quartiles. In order to calculate our first and our third quartile, we have to have our median. So the median represents the middle point. Here we have 10 data points, so we have an even number of data points, which means our median is going to represent the average of our two most middle points. So our median is 19. Once we have our median, we will divide the upper points and our lower points in half, and we calculate the median of each of these halves. Each of these halves has an odd number of data points, so our median will actually be a middle number of those. So in the bottom half, 17, that is our first quartile. 21, this is our third quartile. So our interquartile range then can be reported as either the range of those values, so 17 up to 21, or we can report it as the difference between 21 and 17, which is 4. So we saw how to calculate the interquartile range and the range by hand. Now let's see how we do it in R. So in R, I make my vector, prac2, and to calculate the range, it is as simple as using the range function. I guess it would help if I ran the vector. So 14 to 23. If we wanted to calculate the difference in magnitude from the smallest to the largest, we could use diff of the range to get 9. And this matches what we calculated in R. What about the interquartile range? Well, we can use IQR. And what IQR gives us is the difference between the first quartile and the third quartile. Now that's not what we calculated. So the question is, did we do it incorrectly? Nope. We didn't. If you go back and review a previous presentation, there are actually 9 different ways to calculate quantiles in R based on the type. Those 9 different ways account for duplicate values. It accounts for whether or not we include the median in our quantile calculations and so forth. So here, if we calculated the first and third quartiles, we get different answers than what we would have obtained if we do it by hand. Is that going to be an issue? No. If we do it by hand, I want you to do it the way I showed you. If we do it in R, we just report the values that R calculates. So we've calculated means, variances, interquartile ranges, standard deviations by hand and in R. And I told you that we can also do it in the calculator. How we do it in the calculator just kind of depends on what type of calculator you have. So I have an old school calculator, a Casio VPA-M. Mine kind of looks like this, although it's an older number. It's an older model. I had this calculator since I was in high school, at least, maybe even 7th or 8th grade, and it still works to the day. How we would use it will kind of depends on the models. So I search for mine, and I can actually find my original instruction book. So I have that 115S. All right, so if we wanted to do statistical calculations, this tells me how to go about inputting my data and then calculating different types of statistics, summary statistics. So on my calculator, I can calculate sample size, I can calculate the average, I can calculate the sum of x squared, and do the variance and the standard deviation all in one. Some students have this Casio or another model of Casio, and for the most part, all of the Casios work the same way. Another popular calculator that students have are the Texas Instruments calculator, especially this one, the TI-300XA. All right, this can also do statistical calculations. How you do it? Well, you can download the guidebook or check YouTube. Here's a video that describes the basic statistical operations and how to input data, and then how to calculate different types of summary statistics. And it shows you button by button, so you can kind of follow along and learn as you go. Graphing calculators also have the ability to calculate means and variances and so forth. And I'd suggest that if you have a scientific calculator, you learn how to do this in the calculator. It's a very good check for when you do it by hand, just to make sure that all of your calculations are the same. You don't want to lose a point just because you added something up incorrectly and then got the wrong answer. Another thing I'll note is that with these scientific calculators, you can see that they come with a cover. Mine has a flip top, and usually in that cover there's a piece of cardboard that gives you shortcuts and kind of summarizes how to input your data, or even shortcut keys that tell you what key combinations to use in order to calculate, let's say, the sum of the x squares or the sample size. It's good to have. Once you learn how to do it once, then the shortcuts on the calculator cardboard piece or on the actual cover itself will be very, very useful. If you have questions, bring your calculator and I should be able to help you and show you how to calculate means and standard deviations with your calculator. We've introduced frequency tables as a summary of count data, so discrete data. And we showed you how to calculate means from those frequency tables. We can also calculate standard deviation variances from our frequency tables. The standard deviation and variance utilizes the exact same formulas. However, we now multiply some of our calculations by the frequency in those tables. It's actually not very difficult to do if you make sure to keep all your data in a table. So let's look at how we can do it by hand. So here's an example data set that demonstrates how to calculate summary statistics from a frequency table. Assume this data set came from an experiment. We have cages that have 5 mice in it, and we were interested in the transmissibility of an infectious disease. So we take one mouse, infected it, and then placed it back with the other 4 mice. And then what we recorded was the number of the other mice that actually acquired that infectious disease. So we have two cages where none of those mice acquired an infection, 10 cages where we had 1 mice acquire the infection, 31 cages had 2 mice get infected, 65 cages had 3 out of the 4 infected, and 42 cages had all 4 mice get infected. So our question for this frequency table is what is the mean, what is the variance, and what is the standard deviation? These would be standard questions that I would ask for these frequency tables. So our frequency tables utilize slightly different equations, although they actually mean the same. So our average represents the sum of the frequency times our x values divided by the sum of the frequencies. So the first thing that we're going to do is calculate our average. And to do that, I'm going to calculate this fx column. So I multiply across the row to obtain our f times x values. The sum of the f times x column is 435. So our average is 435 divided by the sum of our frequencies, which is the sum of the f column, and that is 150. So our average is 2.9. We need this average to calculate our variances. Now the equation that we're going to use to calculate the variance must account for the frequencies. So it is the same x minus x bar squared, but what you have to understand is that we do this x minus x bar squared calculation for each value in our data set. And this frequency table represents a vector. So we have 2 values that have 0. So you're going to have 0 minus the mean squared appear twice. You have 1 minus 2.9 squared appearing 10 times because that's a frequency in our vector. So what we can do is do the x minus x bar squared once and multiply by the frequency, and then add up all of those values. Our denominator is the sum of the frequencies minus 1. So there's going to be a couple new columns that we calculate to make the calculation by hand a little bit easier. First, I'm going to do the x minus x bar. And there's a pattern to this. So my x bar is 2.9. 0 minus 2.9 is negative 2.9. And then 1 minus 2.9 is 1.9. Then we have 0.9. And then 3 minus 2.9 is 0.1, and then 1.1, and if we had more, it'd be 2.1, and so forth. So there's a pattern with this x minus x bar. Next, we square each of those values to generate this x minus x bar squared. Now, you can calculate all of these all at once, or you can do what I suggest doing. So we're going to square each of these values. And then what I suggest doing is as soon as you square those values, go ahead and multiply back by the frequency. So that way, we calculate this first value, 8.41. You do that in our calculator. So 2.9 squared, we get 8.41. And while that is on the screen, then we multiply by our frequency, which is 2, to get 16.82. This saves some time because it saves on keystrokes. So second one is 1.9 squared. Just do that on your calculator and you get 3.61. Then while it's on the calculator, we multiply by the frequency, which is 10, and we get 36.10. Next one, it's 0.9 squared. 0.81, and while that is on the calculator, you multiply it by our frequency, 31. Next one is 0.1 squared, which is 0.01, and while that's on the calculator, you multiply it by 65 to get 0.65. And lastly, 1.1 squared is 1.21 multiplied by 42, which is our frequency, and we get 50.82. This is the column that we want. If we sum this column, this gives us the numerator of our variance equation. So when I add up all of these values on the calculator, I get 129.5. So 129.5 divided by the sum of our f's, so our frequencies, is 150 minus 1, which is 149. So our variance for this problem is 0.869. Our standard deviation is just the square root of our variance. So the square root of 0.869, which is 0.932. So if you see this example, go back, see if you could do it by hand, and you get the same answers. So we did this by hand. Now let's do it in R. So here's our example problem data. Remember, with the frequency tables, we have to first convert it to a vector so that we can calculate the standard deviation and the variance. This is the only way to calculate the standard deviation and the variance. So I've created my x vector. It's a vector from 0 to 4, so that's 0, 1, 2, 3, and 4. And then I created my f, which is the frequency column. And then I will create my data. I will just call it dat. And I use the rep function where we repeat the x vector by each of the values in our f vector. Now what I am going to do is just issue the table command to create a data table or a frequency table of that new vector. And when I do that, that just confirms that I have the same frequency table as what was given in our practice problem. So now that we have our data as a vector, so this is convert table to vector, then what we can do is calculate our summary statistics. And the summary statistics are calculated just like we did with a vector. So just the mean of our dat vector, variance of our dat vector, standard deviation of our dat vector. We can calculate the range of our dat vector, the interquartile range of our dat vector, and we can do the median of our dat vector. and anything else that we were interested in calculating. We have a vector. R is going to work with all of it. So everything's going to work. So our mean is 2.9. Our variance is 0.8691275. Standard deviation is 0.93227, which all of those three values agree with what we calculated. The range is simply 0 to 4. Our x's go from 0 to 4. The interquartile range is going to be 2 according to R, and the median is 3. And again, this is the median according to R. So calculating frequency tables by hand really isn't any different than how to do a vector by hand. But once you work in R, the first thing you have to do is convert the frequency table to a vector, and then from that vector you can calculate your summary statistics. So here's a practice frequency table. I want you to calculate these values. Now, what we didn't do is calculate the median and interquartile ranges of a frequency table by hand. We could. I can show you how to do that, but I'm going to say I'm not going to ask you these questions for a frequency table on the exam or on quizzes, so I'm not going to ask you how to do it here. So take this frequency table, calculate the mean, mode, variance, and standard deviation. First do it by hand, and then confirm your work in R. So here's a practice problem where we calculate the mean, variance, and standard deviation in this frequency table. We are going to use our standard equations. So our mean is the sum of the fx over the sum of our frequency column. So the sum of the frequencies is 200. That's the sum of that column. We now need to calculate f times x. So we multiply across the rows. (102), 72, 15, and 12. Once we have that column, we can calculate the sum of the fx column, which is 383. Our average is the sum of that fx column, 383, over the sum of our frequencies. And that gives us 1.915. Now we need this average in order to calculate our variances. Variance that I showed you is kind of a long way, but we will do it here. So the first thing we have to do is calculate that x minus the x bar squared. So x minus x bar, so 0 minus 1.915 is negative 1.915, then 0, 915, that was a negative. And then we have positive 0.085, and from here we just keep adding 1. Here's our pattern. 4.085. Then we take this value and we will square it, and then we will immediately multiply by the frequency. So x minus x bar squared is 3.667, and then I immediately multiply by the frequency to get 88.01. Next one, when I square this value, I get 0.837, immediately multiply it by the frequency to get 46.88. 0.085 squared is 0.007, multiply by the frequency and I get 0.46. 1.085 squared is 1.18, multiply by its frequency, I get 40.03. 2.085 squared is 4.347, multiplied by its frequency is 78.25. 3.085 squared is 9.517 multiplied by its frequency 28.55. 4.085 squared is 16.687 multiplied by its frequency 33.37. So now with that column I will add that up to get the sum of my f x minus x bar squared value, which is the numerator in our variance equation. So our variance is the sum of our frequency times our x minus x bar squared divided by the sum of our frequencies minus 1. So I have 315.55 divided by 199 gives us 1.586. Our standard deviation is the square root of our variance. So it's a square root of 1.586, which is 1.259. Now, there is another way to calculate variance, and it's using that alternative equation. So, our variance equation could be this, x bar squared over sum of the f's minus 1, or we can do it as the sum of the x, or sum of our frequencies, times each of our x's squared minus the sum of our frequencies times our average squared divided by the sum of our frequencies minus 1. In the table, this is probably easier to do because we have our x column already. So our x column is right here. So what we can do is just square each of those values to get our x squared values. And remember, if we were doing this as a vector, each of these points, each of our x's, appear in our data set however many times we specify in our frequency column. So if we take all of our x's and square them, well, we have all of those square values, and they appear however many times the frequency column states. So what we can do is take this x squared value now and multiply it by the frequency to get that sum of the f x squared values. So 252, 306 for this, 288, 75, and 72. Now note, these are whole numbers. We don't have to work with decimals. So if we add up this column, this is the sum of our f x squares values, and we get 1049. Then what we can do is go use this equation to calculate our variances. So our variance would be 1049, which we just calculated, minus the sum of our frequencies, 200, times our average squared, where our average squared is 1.915 squared, divided by the sum of our frequencies minus 1. When we simplify that numerator, we have 1049 minus 733.445 divided by 199, which is 315.555 exact. That gives us our variance of 1.586. So as you can see, there are two different ways to do the variance depending on what equation we want. The long way gives us decimal points. But for some people it's a little bit easier to calculate and to keep track of what's going on, especially if we calculate the sum of squares. Other times it's easier to do this second method because we only have to calculate our x squared values and then multiply those by our frequencies. I don't care which one you do, just as long as you get the correct variance and standard deviation. So we have our values, our mean, variance, and standard deviation that we calculated by hand. Let's do it in R. So just again, emphasize the point. The first thing we have to do is convert these frequency table, the data in this frequency table, into a vector, and then we do our calculations on that vector. So here's my conversion to a vector. I make my x vector, so 0 to 6. I make my frequency vector. All of those appear in a frequency table. And then I create my vector that I'll call dat by using the repeat function. And I issue the table function just to confirm that that's what I get. So I can compare that frequency table to this frequency table. It's in our presentation. And you'll see that I inputted the data correctly. Then for the summary statistics, all that I have to do is issue the mean function, the var function, and the st function on that vector, and I can get all of these data. And as you'll see, I get the exact same numbers. Is there a mode function in R? Yes and no. There is a mode function. It's in a couple different packages, but there is not a built-in mode function in R. So if I try to issue mode of dat, I get this, numeric. What it basically is doing is saying, what is the data type? What does the information look like in that vector? That's not what we mean when we ask, what is the mode of our data? The mode represents the most common data point. We don't have to really calculate. There is no function to calculate, or we don't need the function to calculate because it's just the most common value. So what we can do is just look at the data table itself and see 2 has 63 items, and that is the most that occurs in our data set. So the mode for our data set is 2. There's one more measure of dispersion that we need to talk about, and it's the coefficient of variation. The coefficient of variation takes our standard deviation and expresses it as a percentage of the mean. This estimator is biased. It's going to be below its actual true value. So if we wanted to, we could do a correction factor and calculate an unbiased estimator. We're not going to do that. Instead, what we're going to do is use this equation to calculate the coefficient of variation. Now, why would we do this? If we were interested in variability of two different data sets, then the coefficient of variation is better to use than, say, variance or standard deviation because we scale it against the mean. This is especially important if the means differ. So if we have a mean of 10 versus a mean of 100, yeah, the variances are going to be larger for that mean of 100, but that doesn't necessarily mean that the data are more variable when they have a mean of 100. Also, coefficient of variation allows us to make comparison between variables that differ in their units. It doesn't make sense to compare a standard deviation that has a unit grams versus standard deviation of a unit centimeters. They're two different units. They're not comparable. But if we convert it to the coefficient of variation, so a percentage of variation around that mean, then we can compare these two values. Calculating it by hand is fairly easy. And I'm going to let you do that yourself because you'll have to calculate the mean and the standard deviation. It's good practice to do this by hand. We are going to do this in R. So I have two data sets. Dat1 is a vector, Dat2 is a vector. Our question is, which of these two vectors is more variable? If we were to do it by hand, we calculate the mean and the standard deviation, and then do standard deviation divided by x bar times 100 to get our CV value. Whichever coefficient of variation is larger means that that vector is more variable. When we do it in R, we'll get the exact same answers as if we did it by hand. So, how would we do it? Coefficient of variation. So I'm going to create my vectors first. So dat1, 2.9, 4.5, 4.6. Let's move this up so we can get to it. 4.9, 5.2, 5.3, 5.7, 5.8, 5.9, and 7. There's data 1, data 2. 41, 46, 46, 48, 48, 52, 53, 54, 57, and 66. Alright, so here's our data sets. Those are our vectors. So let's calculate some summary statistics. I am interested in variability. So if I do the standard deviation of dat1 and the standard deviation of dat2, we will see that the standard deviation is larger for vector 2. Well, that's no big surprise. Our values are in the tens. They're around 50. So we have a range of values from 41 to 66. Numerically, we're over 20 units difference from our smallest to the largest value. For data 1, our range is 2.9 to 7, so basically 4 units. So yes, our standard deviation is necessarily large, but that doesn't tell us anything about overall variability. So for that, what we're going to have to do is calculate our CV, our coefficient of variation. So our coefficient of variation is the standard deviation divided by the mean. And then we multiply it by 100 to get a percentage. So for data set 1, our data points exhibit 20.9% variation. That's how much it varies around our mean. How much does data set 2 vary? Well, pause the video, type the code into R, and get it. Alright, so you should have written this equation. So, our coefficient of variation for dataset 2 is 13.73. That's lower than the coefficient of variation for dataset 1. Let's look at these numbers again. Yes, the magnitude of difference is larger. That leads to a larger standard deviation, but relative to the mean, the standard deviation is actually smaller than the standard deviation of dataset 1. So, based on these numbers, we would conclude that DAT1 is actually more variable. Could we do this by hand? Yes. And again, I urge you to practice doing it by hand because you will likely see it again on a quiz or exam. Just remember, you take these data sets, calculate your mean, calculate the standard deviation, and then perform the coefficient of variation calculation. So that wraps up our introduction to descriptive statistics. You've learned how to calculate quite a few of these by hand and using R. So you might be wondering, what do I need to know for the exam? So this slide just kind of tells you that. I want you to know how to calculate by hand and in R the mean, median, mode, variance, standard deviation, interquartile range, the range, and the sample size. I'll note that the mode is simply using the frequency table to figure out the most common value. When working with frequency tables, I want you to be able to calculate the mean, variance, and standard deviation. How you calculate the variance is up to you. You can use the long way, which is the x minus x bar squared equation, or you can do it the slightly easier way, which is the x squares, then multiply by your frequency and add them up, and then finish the sum of the fx squared minus your sum of the frequency times the average squared equation. That was in the example problem. For the means, I want you to know when you would use the arithmetic versus the geometric versus the harmonic means, and also know their relationship. So if we have the geometric mean, know if the arithmetic mean is going to be larger or smaller than it. I also want you to know when you might use the mean versus the median versus the mode. Really, the important part is when would you use the mean or the median. And relatedly, also know when you would use standard deviation versus the interquartile range. This should be pretty easy. If you use the mean, then you should always use standard deviation. If you use the median, you should always use the interquartile range. Also know the relationship for these frequency distributions. So if we are normally distributed, the mean equals the median equals the mode. If we are skewed, then the skewness, whichever side has the excess data points, is going to pull the median towards that the mean towards that direction, and the median, but our mean's going to be pulled more than the median. Also know how to determine which vector or variable is more variable. And so this is using the coefficient of variation. Know how to do that by hand and in R. And then lastly, also know the meaning of some of the R code that we ran. Specifically the set.seed function, what is that doing and why do we do that? Know how we generated some of these random numbers. So just looking at the code, could you tell me what it's doing and how many random data points it's creating? Also know how to create your vectors and how to create convert frequency tables to vectors and so forth. So review your code. Basically what I'm going to ask is stuff that we've used repeatedly. So know what the mean function is and the variance var function and the SD function and so forth. So this wraps up the descriptive statistics. Where we will move to next is probability. And the probability will give us the background information needed to start generating p-values, which are probabilities.